Okay, I'm going to talk about machine learning on Flink with an odd proviso that we're talking about not Flink machine learning. But of course, there's always an asterisk. And you could use Flink machine learning if you want to. It's just we shouldn't have to require it. This idea comes from a discussion that I had at our recent customer advisory board. I polled our customers and asked them, if you're using machine learning, which packages are you using? I wanted to know which one we should support. Maybe two we should support. And the shocking thing to me is among the customers, this is a small sample, but among the customers who were using machine learning at all, the smallest number of packages they were using was 5. The largest was around 12. And I learned 4 new buzzwords that week. And so the lesson to me was not which machine learning package was the best. It is that anybody who tells you that they have the best or that theirs should be used is wrong. It's just guaranteed anymore that unless you can use essentially any machine learning package in your system, you're not using the best. And it doesn't matter which one you're using now, because next week there will be 3 more, and they all have sweet spots. So if you do more than one problem, any single one is probably not good enough. So the talk today is I'm going to talk about what's most important in machine learning systems, what is not the way it seems it ought to be, what sort of cognitive discrepancies do we come up with in this sort of field. And I'm going to talk about how we can, how us, all of us, can improve the situation that we have. Now, here's the traditional view of machine learning. You have data, old data, training data, God-given. It came from I don't know where data. And you use some algorithm, mystical, magical, cut and paste TensorFlow incantation, and you produce a model. Now the model is data there. The square is of course a program. The things without squares are data. So the model is data there, but then we deploy it. That's something the IT guys do, whatever. I'm a data scientist, right? And so the data becomes a program now, and we feed it more data, and it gives us decisions and actions. This is kind of the view of a data scientist who's had a machine learning class, and this is what they made you do in machine learning class, and therefore this is what machine learning is. You can guess by my intonation, it ain't necessarily so. It doesn't work that way. In fact, it doesn't really even kind of sort of work that way. 90+% of the effort in machine learning is not the learning, it's the logistics, or the bullshit is the most part of it. And the plus sign there is where big data comes in, because big data by definition is where the logistics become the dominant part of the problem you're trying to solve. And if the logistics are much larger than they used to be in an ordinary situation, then this is just the first 90%. The second 90% will be due to the big data, and the budget left for machine learning will be nil. So this is the fundamental thing. And there's a bunch of reasons for that. Just getting good training data is actually really, really hard, even if all you have to do is count. Counting is extraordinarily hard. Well, for me, it's hard if I go above 3, but in automated situations, it's extremely hard because you're counting so many things. You're counting so many things in so many contexts. It's difficult to even tell what context things are in. It's hard to know were the counts all ended at the right time and begun at the right time, especially since many times the times are not all at the same time. The first models that you build, of course, can record data, and then you can use that for later things, but you still have that. And then you decide, oh, I needed to look at different kinds of things in the world, and so I have to restart the whole process again. And this new data is different from the old data. So just getting the training data is hard. And getting good training data, of course, requires an absolute massive amount of knowledge about how your domain works. What really is the mechanism? What really are the things that you might want to know? And I have many examples of me trying to do machine learning in real life where I didn't have enough domain knowledge, or nobody did at the time, and we made wrong choices. I'll tell you about some of those. There's also this myth of the model. There is no the model. It is models. There will always be many, many, many models. It's not going to be just one. It's going to be at least dozens. For most of my customers, it's thousands. So you can't just imagine that it's going to be a simple world. So recording this raw data is a big, big deal. It's worth gold to know exactly what your model would have seen if it had been where it would have seen the data. That's huge. If you reconstruct it later, you almost always will have some subtle effect which gives your model training a time machine leak. A great example of this, once I was building an identity fraud model, and we found that if we knew the gender of a person, the fraud rate was much lower. Well, of course, that was because we knew the gender for everybody who had passed the identity fraud test, because we didn't find that out until after we had decided they were a good risk. And so what was happening is our database of here's what we knew was being updated by here's also what we found out after we had made a decision. I'm happy I didn't go to the customer with that one. I mean, there's other times where you go to the customer and you lack domain knowledge. And like one time I built this fraud model. See, here's the fraud column. We were predicting that. We got like 90% accuracy. We are so cool. Customer says, why did you model that column? And I said, well, because it's the fraud column. And they said, yes, that's the fraud analyst column. That's who investigated it. And you could predict that just by when it happened. The column dummy-512 is the column where we put fraud. Why do you call it that? Well, because it's a big database, we could never change the table. We could never alter table. So we immediately put 600 columns onto the database, dummy 1 through 600, and because we knew we would need more columns later, different types and things like that. And so fraud wound up in dummy-512. Why didn't you model that? Who could guess? Obviously. Documentation? No documentation. So that was a great example of domain knowledge I didn't have, so I looked like an ass in front of the customer. It happens. And real validation also, frankly, figuring out whether your model really works is extraordinarily hard as well. This is especially true in modern days, where more and more of the time the models themselves are having a major role in picking which data becomes your training data. Now, this was always true with things like fraud. Fraud models are an old thing now, but if the model said, that's fraud, you would stop the transaction. And since the transaction didn't happen, you wouldn't find out if it was fraud. Only if you let it go forward would you find out. Now, that's even more true, let's say with a recommender. Only things that you recommend are things that you could find out if they were relevant. The things you didn't recommend, you have no idea. And so as you try to validate models, if the thing that's the champion now and that's recording data is picking the training data based on what it knows, then the new model, which is picking other data, which you have no record of, is going to look worse. This is really, really hard to do. Or, you're putting it in an A/B test. You think that's fair. But the new model has 5% of the data, and the old model has 95%. Either you give them both all of the data, in which case the current production model may benefit from a new lousy model that is kind of like a random sampler. Oh, it's so complicated. And so these are some of the things why this is hard, why the logistics become really a big deal. And there are ways to deal with it, but it just, let me say, it's really, really hard. Now, I'm going to turn the talk inside out here. Here are the spoilers. These are the punchlines for the rest of the talk. I'm going to talk about the data. The data is a big deal. Another example, this talk is turning into Stupid things Ted has done. Another stupid thing I did was I built a video recommendation system. Now that was not stupid. That was a good idea. But we did it based on predicting what people would click on. So we very quickly built something which to us looked like a really bad recommender. What it was is a really good spam recommender. Because people click according to what the title is, not according to what the video is. We got the wrong data. And so we built the wrong model. Prioritize. We should always prioritize what we spend our time on. Not necessarily what's our comfort zone, not necessarily the cool stuff, what's going to get us the most bang for the buck or the minute. We need to keep data around. Streams should be persistent. We can't just imagine it's going to go and disappear. We need to measure everything and record the measurements. We need to meta-analyze, not just build the model, not just analyze the data, analyze the performance of the model, the latency, the accuracy. Meta-analyze then what is going on, what is really making things work. Containerize. Now we just saw a talk, 2 talks actually, and one of them said that it would be interesting to put machine learning directly into Flink. Another one said everything we do has to be in a container. Now if it's in a container by itself, it's not inside Flink. And so there's kind of a contradiction in those 2 ideas. If it were inside Flink, it would be best, but if it's containerized, it's most modular. I come down firmly on the containerized side of that question. Oh yeah, and by the way, you probably ought to do some machine learning. But these other things are the big issues. So let's talk about it. The big wins in whatever you're doing are not going to be the algorithms. And this is a sad, sad thing to somebody who studied really hard or went to a Kaggle contest and came out on top, things like that. If you look at almost all of these contests, like you laugh. This is not funny. This is sad. This is tragic. If you look at the Netflix challenge, one of the earliest contest sort of things, from the first week until the end of the contest, well, in the first week, there were about 8% improvement over the baseline. For the next 2 years, there was just barely more than 2 more percent. So 2 years of the best people on the planet made 2% improvement over the 8% that the first guys off the block got. And this is true over and over and over again. Iterating on the model will give you a fraction of a percent or a few percent. Iterating and changing the infrastructure, changing the data that you're working on, changing the problem you're working on will give you 100% improvement. Massive changes. So I mentioned the clicks before and said that was the wrong thing. The right thing was measure when people watch 30 seconds of a video. Measure when they're happy with what they've got. Seems obvious now, seemed obvious about a week later, and it gave us phenomenally good results. We could have spent from then until now or on to eternity modeling clicks, and we would have never gotten a good recommender. By switching to 30-second views, we got it within hours. Another one is ask a better question. I worked on a product recommender, and it was really hard. We worked for months and months and months and barely got 10% improvement. And then one of the guys on the team said, you know, we should be modeling when the new stock becomes available. So they did that. It took, like half a day to model that. And suddenly the recommender was awesomely good. So if you think about it, if you go to a Black Friday sale at 5 o'clock in the afternoon, there's nothing left on the shelves, right? It's just garbage. It's whatever everybody else didn't want. If you build a recommender to recommend, here's a left shoe, you're not going to get any response, and you're never going to get any gain. If you figured out when the sale started, however, and said, I recommend you go there right now and get these beautiful gloves and hat and things like that, then you can get lift. So asking the different question was a much bigger value and a much better use of time. The 17th model revision will give us very little improvement. So we need to think about, prioritize, what are we going to get out of each minute of thinking that we do. We have finite brains. I do. Somebody here probably doesn't. Just ask them. Now, here's another thing you can do, and these are things that nobody talks about to speak of. One is deploy a decoy server. This is a thing that acts as if it's a model, except it doesn't do anything except record its inputs. Since it's in exactly the position that a model is in, the inputs that it records are exactly the model inputs. Dead, certain, correct. And record them into some unmodifiable storage like a stream. You now have real data that you can then use for training. Stored in a streaming, not steaming environment, not in a database, because people could accidentally fix your database for you. You don't want them to do that. Another thing to do is deploy a canary server. Take some model, it's reasonably good, it's maybe not your best, but it's stable. It's the one that you've done. You know how it works and everything. Suppose it's 90% correct. And suppose the new model, after being in production for a week, suddenly disagrees with this 90% correct model 11% of the time. It used to disagree 3% of the time. You know something very severely bad has happened to your new model, probably not the canary. Or if the score distribution on the canary changes, you don't even have to compare it. You know it's stable. You know you've been running it for a year or 2 or 3. You know it's not necessarily your best model, but you know it inside and out. So if its output changes, something bad has changed in your whole data chain. Maybe the data flow has changed. Maybe the customers that are coming in are different. The canary dies, you know the air is bad. That's the idea. And so you can think about this. A decoy and a canary walked into a bar, right? And asked for a bottle of Club Mate. This is a Flink conference. Well, the bartender said, wouldn't you really rather have a stream of it? That's a joke. I just mentioned that so you know when to laugh. But the idea here is that you want those streams, you want those canaries to have good streaming inputs, because if you have a stream that's really a good streaming system, you got a producer there, you got a consumer there. The producer has no idea who the consumer is. They have no idea about the details of how the consumer's implemented. In particular, is the consumer running when the producer is running? Is the consumer running all the time? Is the producer running all the time? Neither one should care about the other one's implementation. This implies that this is persistent. In fact, the producer should not even care if the consumer exists yet. So we can add consumers, and they will get exactly the same thing. And we can add lots and lots of consumers. This is what makes the canary possible. This is what makes the decoy possible, is you have a good streaming layer there. It has to be persistent, performant. If it's not performant, if it's not faster than anything you could do to it, then people will work around it, and you will have every error in your system different. It has to be performant, has to be pervasive. If somebody has to have a committee meeting to have a stream like that, they will not happen. You must make sure it happens, therefore it has to be pervasive and easy as creating a file to get it. So deploy a decoy, deploy a canary. So this is kind of what it looks like. The stream of data is coming in. We have our decoy who's archiving the data. Now, archiving could be in a stream like I've drawn it here, but it might actually be in a file. One of the tricks there is if you sort the file, then the columns change rarely, and it will compress massively. You can often get 50-to-1 compression of data files by doing that. You have a canary. You look at the distribution of output scores. That's just I just made that up, but it looks kind of like that. And you also want to be having your real model compared against the canary. So now you've locked things down, you're testing the infrastructure all the time by looking at known things, comparing against known things, and recording everything that's happening. The results are persistent, the archive is persistent, the inputs, even the raw inputs, are persistent to some degree. And you can now fix problems when they occur, because they will occur. And if you have the data, you can find out what they were, you can recreate them, and you can fix them. And so to do this, of course, you want to be able to put any kind of model here, any kind of model there. Is it Python? Is it Lua? Is it C? Is it Java? Is it Scala? I don't care. I don't want to know. I don't want to care. I want to be able to use everything. So everything should be containerized so people can deliver it accurately. Safe, accurate deployment is key. We need to have all of the input, all of the output follow very stringent conventions, and we need to have the rigging already there to record the metrics, record the metadata about latencies and things like that. So what we're going to wind up with is something like this. The input is coming in, we're going to do some sort of featuring. Now that's very nicely done with Windows and various kinds of stream processing. Those will be fairly raw features because we may generate more of them that are down here, but that are not logically novel. They're just combinations or transformations of the input. So we have the raw data here, we have many models, we have a decoy and an archive, and everything goes into the scores stream. Now the idea here is we want to be able to light up new models at any time and take them away at any time. And we want somebody downstream from here to be deploying a score merely by letting it through. We want to be able to light them up, get them stable, check in the scores thing here that everything is good, that the difference against the canary is small enough, that it looks like it's running well before a customer ever sees anything about this. So we need to be able to pick, and I can show you Thompson sampling afterwards, but we need to be able to pick which model we're going to have. We need to have a rendezvous with the original origin request so we can send the result back to the consumer. And we need to record all kinds of metrics. So there we have what we had before, and we need a rendezvous server out here. The idea is the original input has some sort of key. We may have carried it through. It may not be a separate arrow. And then if it's a call response sort of query, like you ask me if it's fraud, and I have to give you an answer. What happens is your question goes in here, the answer comes out here, and hopefully has your name attached to it so I can give you the answer back to you, not to you. Make sense? So this allows us to build a streaming system which does query response. This is completely appropriate for anything more than like 10 milliseconds. It's pretty appropriate for anything down to around 2 milliseconds response time. But anything above 10, it's just dead on there. The latency will come here, here, and here. You'll have 1 or 2 milliseconds. And then in the modeling level, and the fact that we've done several layers of this, you're going to have some delays in there. You can get it well down below 10, but you can absolutely get it to 10 if your models themselves are relatively fast. Now, you also need, of course, metrics everywhere, and there's appropriate technologies in different places. Flink is great here, Flink is great there. We don't necessarily want these to be inside of Flink. They might have Flink inside them. We want those to be containerized and opaque. So we're going to send data to them via streams. We're going to collect data from them via streams. But Flink itself is not going to control those because we don't know that it's a technology that Flink can control. Go, C, these things are not Flink friendly at this time. So deploying a new model then simply means that the rendezvous starts looking at M1 instead of M3. That's all it means, deploying it after it's running. So all that has to happen is that the rendezvous server starts paying attention. Initially, right after we deploy it, we ignore those scores except for meta-analysis. And then later, the rendezvous service is informed that we should start paying attention to those scores. And it's now live. And of course, we want to bring it live very gently, a little bit at a time, and then commit to it. And we may have a fallback strategy that if M3 doesn't become available within a certain milliseconds, we'll look for M2 and wait for a certain time. Otherwise, we may fall back to M1 or just a constant like it's not fraud. That way we can always make a decision within the SLA that we have. Now, the framework themselves have to be redeployed as well, not as often, I hope. And you can do something like the Chandri-Lamb port, which is used in Flink checkpoints and save points. The dot there is a special transaction we put in to mark where we have flipped over to the new system or the old. Since this is relatively stateless, or at least we can run them in parallel for a long time in order to gather the correct state, or we can load a Flink save point. We can make the state the same. And then this marker transits through the system, and before we process the marker, the top system is in control. After we process the marker, the screen goes blank. After we process the marker, the bottom system becomes in control. So it's processing the marker that controls which way we go. This gives us a seamless failover of a live system to another live system. And that lets us roll over the rollover mechanism itself. So remember, these were the spoilers before, now they're takeaways. And it's the data, we saw that, lots of examples of that. Prioritization is key, persistence is key, measurement is key, meta-analysis, it's consonant there, you know, P, P, M, M, that's to help you out. Containerize, well, I don't have another C, sorry about that. And here's some great resources for practical advice. Suddenly we're beginning to find people who've built models long enough that they're putting up advice columns that really, really represent the real experience in the world. The top one is a list of things from Google. And it's, oh man, I wish I'd had that 25 years ago. A lot of what they say, they have like a list of 40 things. I have a list of like 10 things that I've talked about today. So, but the things that they have on their list are really, really excellent. The second one is similar, and then the bottom one is a feature engineering description that talks about some of the tricks that nobody normally talks about in public, and they're really excellent. So for instance, if you have categorical variables, order them by frequency. That very often gives you an importance weighting that's roughly logarithmic and lets a lot of models work well. So to repeat, and by the way, I've saved 13 minutes for questions. I'm Ted Dunning. I work at MapR. I also work lately at Apache on the board of directors, but I've been involved in open source for a very long time. And I'd love to hear from anybody, everybody, even you, yeah. If there's any questions, just blank look, scares me. Thank you. So we got about 10 minutes for questions. Anybody got a question or a comment or anybody done anything stupider than what I admitted to doing? I mean, I'll tell you an even stupider story if you tell me your stupid story. It's unbelievable what you can do with real data, both ways. It can be so embarrassing. Questions? Who here has built a model that they deployed into production? Who here wants to build a model that they've deployed into, that they will deploy into production? Yeah, there's somebody. He's brave. What do you want to? No. Give it to that brave fellow back there. What do you want to build?
A model of the stream of consciousness.
Ooh. The ground truth is going to be hard there. Yeah. At least for me, it would be very hard. My best conscious moments are when I'm asleep, I think. You know, the cool dreams you have that solve these puzzles that you've been working on. Are you ever more conscious than that? I'm not sure I should try to answer any questions you might have, but I would try. Anybody got a question or a comment there? So back in the room, you were the guy who did the TensorFlow thing, right? Yeah, this what I'm advising is kind of diametrically opposed to what you were doing. in the sense that you were embedding TensorFlow directly into Flink.
I guess I would just say that Flink itself can be containerized.
So you're putting the container around Flink and then Flink around TensorFlow. And I'm saying keep the models outside of Flink and containerize them separately, have Flink drive data to them and pull data from them. What do you think about that dichotomy in approaches?
I guess I would just say that one thing I like about Flink and TensorFlow working together is you can take advantage of the connector model of Flink as sort of like better I/O for TensorFlow.
And also, frankly, you get all of the failover. You don't have, what I've been recommending here is basically kind of build in the failover. You build it, I mean, as opposed to take it from a framework. So mine is somewhat more ghetto, more sleazy than what you were recommending. But to me, that's also been a source of strength over the years. Not really sleaziness, but the fact that I can control and I can warm those up with exquisite control and very explicit manual control. Whereas if it's Flink, I have to trust Flink more. Is that?
Your good advice is humbling.
Great. They didn't say that 20 years ago. Said, what are you talking about? Okay, well, it's an interesting difference. It is kind of two different directions to go. And I don't think we have really, really good answers other than the Google paper said containerize everything, which you could say you did in some sense. But certainly that's good advice, is use those containers, use the abstraction layer that those give you. Ellen. Here comes the microphone. He's moving fast. Look at him go.
I think both of these talks are, beyond my technical level. But one thing I find interesting about that comparison is I think part of what you're saying, Ted, is that there are some situations you're advising that could have advantage, certain kinds of architecture, certain kinds of structure. But I think the bigger message is that there's no single machine learning tool, there's no single machine learning algorithm that fits all purposes, and that ultimately a lot of this goes back to the data itself and the logistics of the data to fit the particular project. And I think that is not unlike the kind of situation that you're describing. So really you're talking about, variations on how to do this, and that gets back to the idea that people have a lot of approaches and a lot of tools.
So we've taken the same axioms in some sense, that the logistics matter a lot, and we should use the best tools. And you took Flink to manage those, and took the machine learning framework as TensorFlow. And I'm taking a little bit more agnostic viewpoint that I have no idea what somebody's going to pick tomorrow, but I know I can put it in a container. I don't know that I can put it in Flink. And so I'm being a little bit more agnostic in that sense. But otherwise, I think we're starting from the same points of view. I shouldn't say right point of view. We agree at least. Whether we're right is a very different question and a much harder one. So what's our time? We are almost out, 3-4 minutes. 2 more questions, comments? I will assign them if you don't ask them. Could be you, could be you. Anybody? Well, we could finish early. The hallway session is always good. Let's do that then.